In this video, we'll be discussing the introduction of the P-series. Now, it's important to understand that we've been slowly developing a list of types of series that we know. We know geometric series, and geometric series are specifically series such that we have some r to the value of to the power of k. It's important to also notice that the r value, we have convergency when r is less than 1. Even if r isn't less than 1, it doesn't imply that it's not geometric. This is a geometric series in all cases. The geometric series that converge is when r is less than 1. The next one we have after that is we've got the telescoping series, and again the telescoping series is a special case. A telescoping series is specifically a series that has multiple terms inside there of some kind of fractions or functions such that we're subtracting or adding them together. So I'm just going to go ahead and do two pieces here with a subtraction sign between them. But again, telescoping is fractional pieces where they slowly partial sum down into something basic. After that, we talked about the harmonic series. The harmonic series is specifically a series that will always diverge, so something of 1 over k. Now, let's talk about what the P-series is. So a geometric series is a number to the power of k, while a P-series is specifically a k to the power of a number. So we generally write the P-series not like this, actually, but like this. So it's 1 over k to the power of p, such that k equals 1 to infinity. So this is your P-series. And you'll also notice that if we look very closely, if p equals to 1, then don't I just have the harmonic series? If p is 1 in this P-series, then I have a harmonic series, and this thing is divergent. So let's come up with a set of rules for this one here. Now, the rules that we end up creating are the rules for understanding that this thing is basically a function x to the power of a number. So if I have x to the power of number, I can use integration on that, and using the integration techniques on that will allow me to develop the rules for how I'm going to work with this. We're going to go ahead and bypass the concepts of some of those rules, and we're just going to go ahead and go with the understandings. If p equals 1, we know we have a harmonic series. So 1 is an important point that separates this from other values. So what if I talk about if p is less than 1 but greater than 0? Again, we're going to try and refer to p as being non-negative numbers, because otherwise it's just going to take this thing and flip it up to the top. So there's really no point in discussing that, because a k to the power of p in the numerator, just like this one right here, that one will almost always diverge if we're talking about whole numbers of p. Again, it will diverge because it will increase without bound. So let's talk about this case right here. What if p is between 0 or 1? Well, if that's the case, that means I'm looking very much similar to the previous example like I did in the last video, such that we were looking at 1 over something in terms of this. Now, this is, again, a very hand-wavy way to do it. I'm kind of going, hey, we did all this kind of information, and now it's going to go ahead and apply here, and it's general understanding of the concept. So the idea is that if I've got something along the lines of this, where this is some pth root of k, then it'll follow very similar processes to evaluating like we did with the integral test. So the integral test does allow us to prove whether or not the P-series will converge or diverge. In the previous example, we concluded that this thing here is divergent. So it's important to note that if I have anything between 1 and 0, including 1, then this P-series is actually going to be divergent. If we follow the same pattern, we go ahead and check to make sure it's, again, always positive, always decreasing, and then continuous, we can go ahead and integrate this function. When integrating this function, we end up with something actually very, very basic. Again, 1 over, if I'm using some variable x to the power of, so let's just go with 3 for a basic example. This is going to increase to x to the power of -3. When I integrate, I'm going to add 1 to the power, so -2 divided by -2. So what this is really going to change into is if this value is p, then it's -p here, and it's -p plus 1. So the form is 1 over x to the power of p, when integrated, converts to a -1 over p plus 1. Sorry, I should rearrange that to be this way. And then on top, you're going to have x to the power of a -p plus 1 still. While if I look at this carefully, as the value of x changes, if I integrate this from, again, 0 to, from 1 to infinity, this piece right here, since it's a negative exponent, will eventually approach 0. So unlike the previous examples, and I'm going to go ahead and write this down, this is the same thing as 1 over a -p plus 1 times x to the, and I'm going to go ahead and move it down to the denominator, but by moving it down to the denominator, that negative shifts and that positive shifts, so it becomes p minus 1. Now, if I evaluate this from, again, my x values of 1 to infinity, plugging in 1 makes this whole thing go to 0. Makes the exponent go to 0, so it's x to the power of 0, which is 1, and this becomes 1 over negative p plus 1 minus, as infinity, this value, well, x to the power of infinity is going to go to 0. This whole term is going to go to 0, so minus 0. So I can argue then that using the x to the power of 3 as a logical concept of how this transitions, and actually transitioning it using any generic p-value such that the p-value correlates to a whole number that was positive to begin with, or a number larger than 1 such that it transitions to this setup, then we're going to be left with just this value right here. So what we can conclude is that the p-series will converge if p happens to be greater than 1. Again, doesn't converge for equal to 1 because that's a harmonic. It doesn't converge for less than 1 because that behaves very much to a radical like this example back here, and the integral test will prove that. But then if p is greater than 1, the integral test, you'll notice, again, shows us that it will converge to an actual number. Now, let me make one more clear statement on the integral test, is that just because this thing right here converged to this number right here does not mean that this series right here will be equal to this value over here. Again, the integral test says it will do the same thing. It doesn't say that it's going to be equal to the same number. So this is the p-series, and again, the p-series is actually relatively easily used. So if we were to start looking at a couple of examples of the p-series, we might look at something that looks like this: the summation of k equals 1 to infinity of 1 over the 4th root of k to the power of 3. Well, this is a p-series, and it's a p-series such that if I manipulate it a little bit so that I can see it more appropriately algebraically, it's k to the power of 3 over 4. Again, the root goes into the denominator of the exponent. This particular p-value is actually less than that of a whole number. It's less than 1. So by the p-series, or just because of it being a p-series, by a p-series test or p-series, this series, the series of 1 over the 4th root of k to the power of 3, is divergent. Again, given p is less than 1 greater than 0. Another example we might be able to look at is the summation of k equals 4 to infinity. Now, the importance of this example shouldn't be lost on you in respect to the fact that what I'm looking at right now is not an exact p-series. This right here is not exactly a p-series. It's a manipulation of one. So what I'm going to do is I'm going to go ahead and utilize the skills that I've learned about how to manipulate summations, and I'm going to shift this summation. So I'm going to change this to be the summation of 1 over k squared. But if I do that, that means that when I plug in 4, I'm supposed to start with 3 in here. So if I remove the negative 1 from here, that means that I should be starting at k equals 3 instead of 4. Now this doesn't actually change the value of the series, and it doesn't actually change the starting term of the series. What it's doing is it's changing the way that the overall series will appear. That way I can look at the sequence in this form as opposed to in this form. So with this being done, I can then say, hey, this is nothing more than a p-series with p equal to 2, which is greater than 1. Therefore, and again, 3 dots in that form. Therefore, the series 1 over k minus 1 squared from k equals 4 to infinity is convergent. Again, there's no statements about what it's convergent to, just that it is convergent. Again, if you don't feel comfortable stating this using the p-series rules, you can prove this using the integration techniques. They will work hand in hand.